Today in this video, we're going to be picking up where we left off with the multiplication rule. We're going to extend that now to talk about complements, and we're going to add to what I've got so far with conditional probability. Let's do a little bit of review here. Complementary events. Complementary events, the short version is it's two things whose probabilities add up to 100%. If you added this plus a to that side, you'd have a 1 all by itself here. That's 100%. And that's kind of actually a good way to think about complementary, is they add up to 100%. The addition rule, which went with the word or, is you're going to add the two probabilities together. If there is any overlap, there doesn't always have to be, but if there is, you need to subtract out the overlapping probability. The multiplication rule, what we've covered so far, is the probability of A and B, so this is the word and, is the probability of A times the probability of B given A has already occurred. Now, this part of it's not going to change, but we are going to add to what we are using for our conditional probability to look at a little bit more complicated versions. To start off, though, we're going to take a look at the term at least. At least is equivalent to saying one or more. So the idea of it is the complement of getting at least one of something is that you get none of something. Now, typically when we're trying to calculate the probability of at least one, we're going to use this idea that at least one and none are complementary events. So if we calculate the complementary of something not happening and then subtract it from 100%, the complement, we get the probability of at least one of that event occurring. In a form of an equation, it would look like this. The probability of getting at least one is 1 minus the probability of getting none. Or you might see this written as the probability of at least one with the bar over the top. The bar over the top means not. And so you're going to see stuff like that here. Let's say that we toss a coin twice and we want to find the probability of getting at least one. Well, the probability of not getting a tails on the first toss is, of course, 1 out of 2. So the probability of not getting a tails both times would be 1 out of 2 times 1 out of 2, which is 1 out of 4. So then the probability of getting at least one is going to be 1 minus 1 out of 4. So this is the probability of not getting it at all. So 1 minus that would give us the probability that at least one time we get it. So 1 minus a fourth is 3/4 or 75% probability. Let's take a look at one involving people having children. Say you've got a family like this, and you've got 4 kids, and someone says, well, what's the probability of a couple having at least one girl among 4? Well, again, the way we're going to approach this is we're going to find the probability of not having any girls, and then we'll subtract that from 1 so that we can find the complement, because the complement of at least one is going to be the none situation. So we'll go through and we'll calculate. Here's the probability of not having any girls at all, is really what this is saying. Well, it's 1 out of 2 times 1 out of 2 times 1 out of 2 times 1 out of 2. There's a 1 out of 16 probability of not having any girls at all. And by the way, it really doesn't matter what the sex is here. You could give the same exact question for boys or girls. It doesn't matter. The numbers don't really change. Now, the probability of having at least one girl is going to be 1 minus the probability of none. So there's 15/16th probability of having at least one girl if you have 4 children. Let's take a look at another one here. And this one I'm going to approach it a little bit different as far as how to solve this one. The rock and roller coaster at Disney's MGM Studios in Orlando has 2 seats in each of 12 rows. Okay, so we've got, this is a picture of it right here. It's going to have 2 seats there and 2 seats there and so on and so forth. Riders are assigned to the seats in the order that they arrive. So we're going to assume a little bit of randomness here. This might not quite be random. You always get the people that are running to beat somebody. Let's just assume some randomness though here. If you ride this roller coaster once, What is the probability of getting the coveted first row? Everybody wants the front of this. It's an old Cadillac, I believe is what it is. Everybody wants to sit in the front. They want to be in the driver's seat. So what's the probability of getting that front? How many times, and then this is a second question, how many times would you have to ride to have at least a 95% chance that you got that at least once? Okay, so I kept coming back over and over and over again. How many times would I have to come back to give me a 95% chance that I got to sit there at least once? And I'm going to show you a different way of solving that second part there. Well, let's just look at some basics here. The probability of getting it randomly would be, of course, 1 out of the 12. And so that's 8.3%. Not on the first row, well, that's going to be 1 minus that, which is, of course, 91.7% chance. If you wrote it 10 times, well, then it's going to be this times itself 10 times, which actually is going to give us a 42% chance if you switch it over to percent. And so the chance of the first row, so that's not, is 58% chance. What about 20 times? Okay, so here's the, again, this is not the first row, 20 times. It's getting pretty small chance, there's no. So then the chances of having ridden it is 1 minus that, which gives us a growing chance. And of course, where I'm going with this, okay, after 10, there's my probability of getting it once. After 20, there's my probability of getting it at least once. I'll put it that way. But I want to know, when is it going to be 95%? Here's a different way of going about this. If you write yourself a little equation, and all I'm doing here is I'm doing just the equation of what we've been doing. We did 1 minus 0.917 to the 10th, 1 minus 0.917 to the 20th. Let's just do 1 minus 0.917 to the x. And then graph it. This is the graph of it right there. And if you analyze the graph, you'll see up here at 95%, 0.95, it intersects at about, it's about 34.5, probably want to round that a little bit, somewhere in that ballpark. So let's say at about 35 times. So if this is completely random, then you've got a 95% chance that at least one of the times you got the front, if you wrote it about 35 times. Now, I will tell you that you won't be able to ride it 35 times in a day because the lines are long enough. You spend there's not enough hours in the day to get that. But maybe you come back time after time for like a 3-day vacation or something like that. But that's how you would do something like that. A little different approach. You let the graph kind of help you work it out. You may never thought of using graphs for probability, but that is a technique. That is a valid technique. Okay, let's go back and visit conditional probability again. Conditional probability, this is the formal conditional probability. I told you we're going to be tweaking a little bit. So you need to write this down. The probability of B given A is the probability of A and B. That's the overlapping probability. Divided by the probability of A. That's, notice the second part. Conditional probability, formal conditional probability. Probability of B given A is the probability of A and B. That's the intersection or the overlap between the probabilities. Divided by the probability of A, which is always the second thing there. Where probability of B given A is the probability of B given of A has already occurred. I used that phrase earlier. This is when the probability of one event is affected by knowledge of other circumstances. We already know something else occurred. So that I only say that because sometimes that comes up in like a word problem type thing. They'll say something about they already know something. Well, that's knowledge of other circumstances. And when they say that, they're usually giving you a probability, a number, which means you probably need to use that number. Okay, so let's take a look at something here. We do have an intuitive, it's called the intuitive approach. I mentioned that this was the overlap. And the second thing is what's given. So you can think of this in just conceptually. That's what the intuitive means. Kind of from a conceptual point of view, if you figure out what the probability of the overlap is, divided by the probability of what's given, that's the same thing as this formal conditional probability formula. Okay, so let's take a look at something here. The probability of a king given a heart. Well, the probability of a king of hearts is 1 out of 52. The probability of hearts is 13 out of 52. Notice that when you flip over the bottom and multiply, because you're going to have to do that, you've got a fraction over a fraction, you're going to have to multiply by the reciprocal. When you flip it over to multiply, those 52s actually end up canceling out. So it's going to be just 1 out of 13. And you might actually have already thought, well, I already knew that. You were using the intuitive approach. If you think about, okay, if I already know it's a heart, well, there's 13 hearts in a deck, and I'm just looking at what's the probability of the king. Well, it'd be one of those 13, which is exactly right. That's the intuitive approach. I didn't actually use the formula per se. You might refer to this as the common sense. Because some of these questions you can calculate out just using some common sense. In math, though, they typically use the term intuitive, not common sense. But it should follow. There'll be things like this that you can actually just quickly come up with all on your own. Okay, so keep the intuitive approach in mind. Sometimes it's helpful. Let's take a look at this. The risk of a male developing any kind of cancer in their lifetime is 40.14%. So just any, lung cancer, bone cancer, blood cancer, whatever. Of those that develop cancer, so given that they've developed cancer, and are terminal, it is 8.56%. Okay, so they've developed cancer and they're going to be terminal. 8.56% is what their probability is. So a man goes to the doctor comes and says, hey, I got some bad news for you. We've determined you have cancer. Typically the next question is going to be, well, doctor, what's my chances here? What's my probability? Typically what they're talking about would be the probability of survival. Well, what they're really asking in terms of conditional probability is, what's the probability of them being terminal given that they know they have cancer? Well, first you take the overlap, which is right here. This is the probability of developing cancer and being terminal, divided by the given thing. The given thing was they have cancer. Some kind of cancer, any kind of cancer. By the way, I looked this up on the American Cancer Society website. That's where I got these numbers from, just so you know. So this would be it right here. So 21.34% chance that probability of being terminal, so they're going to pass away from it, given that they have cancer. Which, it's not great, but I think about then what's the probability of not being terminal? Well, it would be the opposite of that, which would be 100% minus. That's about 79% chance that they're going to survive. So that would be the positive way of looking at it. Polygraph machines. Polygraph test, those machines where the people look at the screen and they tell by your reactions whether you're lying or not. I'll be honest, I don't really understand how that all works. I don't know what the indicators are, but I do know that from watching movies, polygraphs are those things that check whether or not people are lying. And I know that in some government agencies, they do this. Honestly, it's not for like spy stuff as much as it's when they go to hire you to see if you're an honest person. I think that's what they're used for most of the time. Well, there was a study done here, and I want you to take a look at this chart here a little bit so that you understand what you're looking at. In this row, we are looking at positive test results, which means the polygraph test indicated that the subject lied. So positive in this case, positive means the test says they lied. Negative, of course, means that the test said they didn't lie. Okay, so the test said they didn't lie. Now you have to understand, for almost all tests, and including medical tests, you have what are called false positives and false negatives. So the idea of a false positive would be, hey, it said it lied, but I didn't actually lie. Or a false negative, it said I didn't lie, but I actually did. And so that's what we're looking at here with this chart. A false positive, so it said they lied, but they actually didn't. It's 15. True positive, the machine said they lied, and yes, they lied. So this column here is they did not actually lie. This column is they did actually lie. Okay, so we're going to look at some probabilities here. The probability of a positive test result given that the subject lied. Okay, so a probability of a positive test result given that the subject lied. Okay, so what you're going to need for this is you want to know how many people lied. And if you take the 42 plus the 9, that gives you 51. And you'll see here at 51, that's where I'm coming from. The total number of people that lied. So the number that lied and are positive, I'm just looking at the intersection of my row and my column, which is of course 42. Divided by, now this is the part that's tricky typically. What do you divide by? And it's divided by the sum of the second thing here that they lied. So that's why I wanted to get that 51. And there would be the probability that there. The probability that the test said they lied and they actually did lie. 82%. Which, all in all, 82, 83 in that ballpark. I guess it's okay. I wouldn't want to be one of the other people because that means there's like 17% of the people that it's not working so well for. If I use the formal definition, so this was the intuitive approach. This was an intuitive approach to conditional probability, and you have to understand that you're going to need one of the numbers that comes from the second part. If I use the formal definition, well then it's going to look like this. There's 98 people total, so you got to add up all the people. There's 98 total here. And it's the probability of the intersection, okay, the A and B, which is the intersection. So row intersecting column is 42 of the 98, and that's this one right here, divided by the probability of the given thing. Well, the given thing is that they lied, which was 51 of the 98. But notice here, when you flip over the bottom fraction and multiply, the 98s are going to cancel out anyways, which leads us right back to the intuitive approach, and we get the same thing. So if you can keep track of the intuitive approach, it works fairly nice. But if you're a rule follower, like, no, I just give me the recipe, tell me how to do it, this is the way for you to do it right here. Like I said, the common sense one is fairly simple. At the same time, some people have trouble thinking that way. They'd much rather just follow the recipe, in which case do that. Let's take a look at some more conditional probabilities. Here's some information. The probability that an airplane flight departs on time is 89%. The probability that the airplane flight arrives on time is 87%. So leaving on time, arriving on time. You'd think they'd be the same, but of course they're not. I suppose there's, factors that can affect them up in the air, wind or something changes. I'm not sure. The probability that the airplane departs and arrives, notice this is an overlap, there's an and here, and arrives, is 83%. Now we can take a look at some different conditional probabilities. Find the probability that a flight departs on time given that it arrives on time. I'm going to do this one, then I'm going to ask you to pause and do the next one. So, probability that departs on time given that it arrives on time. You want to take the overlap. Okay, this is kind of more the intuitive approach here. Departs and arrives on time, divided by the given thing that it arrives on time, which was the 87%. You divide and you end up with 95.4% probability. Okay, why don't you pause this and you try this one. Find the probability that a flight arrives on time given that it's departed on time. All right, hopefully you came up with this. 93.3% probability right there for that one. I'd like you to read an article. It's on page 181 called Confusion of the Inverse. Please read through that, and there's some problems to take a look at. Have a good day.